You know that incredible, chaotic, violent display? A lightning strike. What if I told you it isn't random at all? Today, we're going to break down the exact, step-by-step recipe that turns a simple cloud into one of the most powerful forces on the planet.
Yeah, you heard that right. And that's maybe the biggest thing to wrap your head around. And it might just blow your mind. Lightning is not a random act of nature. Not even close.
Actually, every single bolt follows this incredibly specific, predictable recipe. So in this explainer, we're going to walk through that recipe together, step by step, and really see how a cloud can unleash all that crazy energy. So what are the ingredients, right?
Okay, so our story really begins with this invisible force. It's the basic recipe for the thunderstorm itself. This is ground zero, you know? High up in the atmosphere, this is where all that potential for a lightning strike starts to build.
And to really get how this force builds up, we've got to go deep inside what you could call the storm's engine. We're about to see exactly how this huge cloud of water and ice literally turns itself into a giant floating battery, just waiting for the moment to let go.
And right at the heart of this engine, that's the cumulonimbus cloud. Now, these are not your everyday puffy little white clouds. No way. These things are towering, super volatile giants that can stretch for miles up into the sky. And get this, they can contain the energy of several atomic bombs. This is literally where lightning is born.
So you're probably wondering, how does this battery even get its charge? Well, it all boils down to a process called charge separation. Inside that cloud, it's just this chaotic dance, right? You've got these powerful updrafts pushing light little ice crystals up, and they're crashing into heavier ice particles that are falling down. And in these millions and millions of tiny collisions, electrons get knocked loose, they get stripped away. And this creates a massive electrical imbalance. The lighter particles that keep going up, they become positive. The heavier ones that are falling, they become negative. And just like that, the cloud starts sorting itself into these really powerful electrical zones.
Now, this separation process, it isn't just some neat little atmospheric tidying up. No, it's creating this growing electrical tension. You have this invisible but really powerful connection starting to form between the sky and the ground way down below.
And here's what that looks like. You get this massive electrical opposition. The bottom of the cloud becomes super negative, and in response to that, the ground right underneath it becomes positively charged. I mean, it's the classic case of opposites attract, just, on a totally epic scale.
So this whole standoff, it creates this incredibly powerful, invisible electric field between the cloud and the ground. And a great way to picture it is like a giant rubber band that's just being stretched and stretched and stretched, storing more and more potential energy with every single second.
And eventually, you know what happens? That tension just becomes too much. The atmosphere can't contain it anymore. The electric field gets so strong that it literally breaks down the air's ability to insulate. This is the moment. This is the breaking point.
So the first move is this thing called a stepped leader. And it's basically a channel of negative charge that starts to snake its way down from the cloud. It's moving at over 200,000 miles per hour. But it doesn't move in one smooth line. No, it travels in these short, rapid 50-meter jumps. It's like it's feeling its way out, searching for the absolute path of least resistance to the ground.
Okay, so at the exact same time as that negative leader is getting closer and closer, that powerful electric field starts pulling positive charges upward from the ground. These are called streamers, and they start rising up from anything tall. Trees, buildings, even people. They're literally reaching up for the sky, trying to make that connection. And then, bam! This is the climax. The moment a downward leader finally connects with one of those upward streamers, the circuit is complete. And instantly, a massive electrical current just flows along this brand new channel. That is the brilliant flash we see as a lightning bolt.
So, that's it. The circuit is complete, the strike is made, but what about the incredible show that comes with it? Let's dive into the science behind that iconic flash and, of course, that thunderous boom we all know so well.
Okay, get ready for this, because this fact is absolutely mind-blowing. For just a fraction of a second, the air inside that lightning channel gets heated to a temperature that is hotter than the surface of the sun. Can you even imagine that? It's just an unbelievable amount of energy being released in a teeny tiny space.
And that intense heat, it's the reason for everything we see and hear. That brilliant flash of light, that's just the air in the channel glowing because it's being superheated by all that electricity. And the thunder, Well, that's the sound of that same air expanding violently. We're talking faster than the speed of sound, which creates a massive shock wave that just booms outward.
All right, so now that we've basically built a lightning strike from the ground up, let's zoom out a little bit. Because understanding its power and its danger is so key to predicting it. And it's also really important to remember, not all lightning is the same.
And here's another thing that might surprise you. You know the lightning we all think of, the kind that actually hits the ground? It's actually the minority, by a lot. A full 75% of all lightning just happens inside a cloud or jumps from one cloud to another. Only about a quarter of all lightning ever actually touches the ground.
But that 25% is incredibly dangerous. We're talking millions of volts in a single strike. That's enough power to start fires, destroy buildings, and take out entire power grids. And since electricity is always looking for the shortest path, yeah, tall objects are at a much higher risk of getting hit.
So what's the big deal? Why does all this matter? Well, because understanding these mechanics, from that first charge separation all the way to the final strike, is absolutely crucial. It's what lets meteorologists build better storm prediction models, and it helps all of us create better safety plans to protect people and property.
So I think the biggest takeaway here is really a whole new way of looking at it. The next time you see a thunderstorm rolling in, just remember, you're not just watching wind and rain. You're literally watching a massive, powerful electrical system playing out right over your head.
It really makes you wonder, doesn't it? I mean, if a simple storm cloud is basically a giant electrical engine, what other powerful, invisible forces are out there, all around us, shaping our world in ways we can't even see?